Welcome students to the MOOCs series of lectures on non-parametric statistical inference. This is lecture number 10 and also this is going to be the last lecture of this series. At the end of the last class, I said that I will continue with different algorithms in this class. In particular, we shall study 4 different tests, namely permutation test, which is used for comparing the distributions of two populations; Fisher's exact test, which is used for comparing binomial populations or two binomial populations, and we shall see that it is an extension of the permutation test. Then I shall talk about Kruskal-Wallis test. It is different from the earlier ones in the sense that here we will be comparing more than two populations. That is, we shall focus on the distributions of more than two populations, and then we will go to JT test, which is a variation of the above. That means, here also we shall compare more than two population distributions. So, let us begin with permutation test. So, the background is very familiar. We have two samples x and y of sizes m and n, and with sample means mu x and mu y respectively. To test the null hypothesis H naught, that x and y have come from the same distribution. So, it is the same problem. We are comparing the distribution of two different populations and we are checking whether they can be considered to be coming from the same distribution or not. This works well for small sample sizes. The test statistic T is mu x minus mu y, that is the difference of the sample means. Under the null hypothesis, exchangeability is justified. So, it is a new term that we are coming across. I am explaining what it is. No distributional assumptions are needed. Therefore, we are not assuming anything about the distributions, but reject H naught at a significance level alpha when the observed value of the test statistic T is extreme relative to H 1, that is the alternative hypothesis. Extreme means, since we are considering mu x minus mu y, if mu x minus mu y is significantly greater than 0, that means in the direction of positive, and if it is significantly less than 0, that means in the direction of the negative, then depending upon the alternative hypothesis, we will have to reject the null H naught. Now, the question is, how do we calculate the null distribution of T? It is calculated by finding the values of T for all possible rearrangements of the combined sample of size m plus n into the two groups x and y of sizes m and n. What does it mean? Suppose this is my x and there are certain observations, and this is my y and there are certain observations. Now, if x and y are coming from the same distribution, then each possible x could have been a member of y and each possible y could have been a member of x. That is, this total m plus n many observations we could permute among themselves such that here comes m and here comes n of them, and under the null hypothesis they should all be equally likely. This is what is exchangeability. That means, any x observation can be exchanged with an y observation and vice versa. So, the following example illustrates the concept in a better way. Select 4 students from a class and randomly divide them into two groups of 2 following the curriculum A and B. That means, there are 4 persons and we are dividing it into two groups of 2 and 2. Suppose we could divide it like that, and suppose these 2 are following curriculum A and these 2 are following curriculum B. Now, the average that we got is for group A, since individual scores are 92 and 65.4, the average coming out to be 78.7. On the other hand, the group B students, they have scored 73.5 and 91.9, and their mean has come out to be 82.7. Therefore, the observed value of t, which we are calling say t naught, is coming out to be the difference mu a minus mu b, which is coming out to be minus 4.0. Now, we want to test under the null hypothesis that there is no difference in grades from the two curricula. That means, which are coming from this population, as students are who are coming from this population, there is no variation in their grades. That is, under the null hypothesis, since we are checking the equality of central location, we are looking at H naught is mu a is equal to mu b, and what is going to be the alternative? Looking at these, we feel that the average of A is less than the average of B. Therefore, for this particular problem, we can choose that H 1 is equal to mu A less than mu B. That is, the curriculum B improves the grades as compared to the curriculum A. Since under H naught the observations are exchangeable, we can permute or shuffle the observations, and hence an A observation could be an observation from B also and vice versa. So, this is what I was talking about, that this is what is called the exchangeability. An element of A could have come from B as well as an element of B could have come from A. However, we have to remember that the M and N, these are the numbers corresponding to the population A and corresponding to population B respectively. So, only thing is that that has to be maintained. Therefore, under H naught all the 6 permutations are equally likely. Why 6 permutations? Because factorial 4 upon factorial 2 into factorial 2, that is going to be the total number of arrangements, and that gives us 6 many different permutations. The null hypothesis tends to be rejected if the observed value is extreme in the direction of the alternative H 1. That means, we shall check if the difference mu A minus mu B is too small, or that is absolute value is very large in the negative direction, and if that happens, then we will check how rare the observed statistic is to reject H naught in favor of H 1. That is the normal thing we do. We look at this, how rare it is, what is the probability of getting this value. If that is too small, then we are going to reject the null hypothesis. We will assume that actually mu A is giving lower performance in terms of grade improvement in comparison with the curriculum B. The p value of the test is the proportion of permutations having the test statistic value more extreme or as extreme as the observed value in the direction of the alternative. So, with that, let us check the following table. We have computed for these observations all the 6 permutations. What does it mean? The first row says that these 2 could have been observations from A and these 2 could have been observations from B, whereas permutation 2 is saying that these and these are coming from observation A and these 2 are coming from observation B, the middle 2 65.4 and 73.5. So, like that for all the 6 permutations we have computed what is going to be the mu A and what is going to be the mu B. And we have computed the value of the statistic T for all the 6 permutations. What is the advantage? This gives us the probability of getting one particular value of T. Therefore, the obtained value of P is probability T is less than equal to T naught. Our T naught has come out to be minus 4. Therefore, how many of them are less than equal to minus 4? 1, 2 and 3. Therefore, that probability is coming out to be 3 by 6 is equal to 0.5. Thus, by complete enumeration, we can obtain the p value for a given problem. Quite naturally, we can do it only when the number m and n are quite small. Of course, if they are very large, then we have to go to computer programming. In general, under H naught, since the rearrangement into groups is possible, we can calculate the exact null distribution of the test statistic as we have computed here. The p value for one-sided alternative hypothesis is calculated as the proportion of permutations having the test statistic value more extreme or as extreme as the observed value in the direction of the hypothesis, which we have said before. Therefore, if the alternative is mu x is less than mu y, then p value is probability t less than equal to t naught. If the alternative is mu x is greater than mu y, then p value is probability t greater than equal to t naught. However, if the alternative is two-sided, that is mu x not equal to mu y, then we shall look at the absolute value of t greater than equal to the absolute value of the t naught that we have got and what is the probability for that one. For this case, our alternative was that mu a is less than mu b, therefore, we will stick to this one. And we have calculated that this probability is coming out to be 3 by 6 is equal to 0.5. Similarly, if the alternative would have been mu x greater than mu y, that is mu a greater than mu b, then that would have given us the value 0.67 for p, and if would have looked at probability of modulus of t greater than equal to modulus of t naught, that would have given us the value 1. The example is there to show the computation needed for carrying out a permutation test. Due to the small values of m and n, that is we have taken only 2 and 2, the probabilities coming out to be very high. This is because the total number of permutation is 6, therefore, the minimum probability that we will get for any event is 1 by 6. It cannot be less than that. That itself is pretty high to reject the null hypothesis at say 5% level of significance. But for slightly higher value of m and n, say suppose we have taken 5 and 6 to be the sample sizes from the two populations, then the smallest probability may come out to be 1 upon 462, which is 0.002, and therefore, when we apply permutation test there, we could get some meaningful result even at 5% level or 1% level of significance. Let us now go to the next test, which is called Fisher's exact test. As I said earlier, here also we shall use the permutation test, but in a slightly more tricky way, as we see, as Fisher's exact test is for comparing two binomial populations. So, what is Fisher's test? It is a case where an experiment is designed to test a human's ability to identify or to discriminate correctly between two objects, a success and a failure. When the subject is told in advance exactly how many successes are there in the two samples combined. Complicated, but you will understand what I mean. The subject's job is to allocate the total number of successes between the two groups, that is to indicate how many successes are there in each population given the total number of success. So, suppose as before there is A population and there is B population of size say m and n, and there are some success and failure here and some success and failure here, and we want to check if there is any difference between the success rate of A and B. What is given to us that total out of m plus n many elements, how many successes are there. Based on that, if we have the ability to actually discriminate how many of them are real success and how many of them are failure. So, what does it interpret to? So, suppose there are m tosses of a coin 1 and n tosses of coin 2. Let A and B denote their outputs. Let x and y are the random variables denoting the number of heads respectively. So, suppose there are m tosses here and n tosses here. Therefore, the number of heads could be 0, 1, 2 up to m, and number of heads here could be 0, 1, 2 up to n. It is given that there are x many heads here and there are y many heads here in second population. What does it mean? We are giving that out of m plus n trials, there are x plus y many success, that is heads. We want to test whether the probability of getting an H is same for both the coins A and B. So, permutation test can be used for this problem for any sample sizes when the marginal column totals x plus y for success and n minus x plus y for failure are assumed to be fixed. So, in some sense we are also using the permutation test for testing the association of the two binomial populations. So, consider two independent samples of sizes m and n from two binomial populations A and B with probability of success being P 1 and P 2 respectively. They need not be equal, whether we can guess it or not. If we guess, then we will give equal to both of them, but whether we could guess the actual probabilities or not, that is the question. Let the observed number of successes be x and y. So, what we are saying that this data can be represented in a tabular form. There are out of m trials x success and a minus x failure for the first population. Out of n trials there are y many success and n minus y many failure for the second population. Therefore, in total we have x plus y many success, n minus x plus y many failure, where capital N is small m plus small n is the total number of samples. In the 2 cross 2 table, the marginal row totals are fixed at the two given sample sizes and also x plus y is given. Therefore, given x, we can easily determine the remaining 3 values. Because we are given m and n, these are fixed, and also we are given x plus y. Therefore, there is only one independent value, let us call it x, because the moment we know x, we know what is m minus x, we know what is y, and of course, therefore, we know what is n minus y. That is what we are saying, that given the value of x, it determines the remaining 3 values once x plus y is fixed. Under the null hypothesis, P 1 is equal to P 2 is equal to P. Then the conditional distribution of x given the marginal totals follows a hypergeometric distribution. That means, what is going to be the probability of x out of m many trials? That is going to be m c x n c y, the product, divided by capital N C x plus y. This happens because under the null hypothesis that P 1 is equal to P 2 is equal to P, the sum of x plus y itself is also a binomial random variable with parameters m plus n and p. To obtain the p value, we use permutation test with x as the test statistic. To find the permutations of the 2 cross 2 tables, keeping the row and column totals fixed at their presently observed values. That means, whatever value is given to us for x plus y, that will keep fixed, and therefore, we should be able to interchange x and y observations among themselves, keeping m, n and x plus y fixed. Then H naught is rejected depending upon the alternative by obtaining how extreme the currently observed value x is in the appropriate direction among all the possible tables with the same marginal totals. The more extreme it is, the more is the evidence against the null hypothesis. I will give you an example, you will understand it right now. So, let us consider that m is equal to 100 and n is equal to 120, x is equal to 60 and y is equal to 50. That means, if we look at the earlier table, we will get something like this. There are 100 many trials for the first one and 120 many trials for the second one. We have got 60 heads here, and therefore, we have got 40 failures here. We have got total 110 many success, therefore, 50 many heads here, and therefore, 70 many tails here, and this is also going to be 110. So, this is the table that we could construct. We shall reject H naught in favor of H 1, since we are testing P 1 is greater than P 2, as we can see that more number or more proportion of trials are ending in head for the first population. Therefore, what we are suspecting that the probability of success may be more for the first population than the second one. Therefore, we are testing the equality of the proportions against the alternative hypothesis that P 1 is greater than P 2, such that x plus y is equal to 110. Therefore, the exact p value can be calculated from all possible 2 cross 2 tables with the same marginal totals as the observed one, but having a value of x as extreme as or more than the observed value of x. For example, one possible table could have been 61, 39, 49 and 71, then that would have given us again 110 and 110. Like that we could go, perhaps maximum that we could do is 100, 0, 10 and 110, and then we also get 110, 110. So, this is extreme, this could have been one possibility. Of course, some other possibility could have been that there are only 50 heads and 50 tails for the first one and 60 heads and 60 tails for the second one. As you can understand that there can be many possible ways we could exchange the x and y observations under the constraint that this row total is 100, this row total is 120, this column total is 110 and this column total is also 110. Therefore, we shall actually be doing a permutations of all the possible values and then we will try to see what is the probability of the obtained configuration of the table. Therefore, in general H 1 if P 1 is greater than P 2, then H naught should be rejected if the value of x is greater than some threshold. Similarly, if P 1 is less than P 2, we shall reject the null hypothesis if the value of x is less than some threshold T 2, and for the two sided case we will look at whether x is greater than some threshold or x is less than some threshold T 4, and the values of the thresholds will depend upon the level of significance alpha. That of course, all of us understand. Let me illustrate the same from Professor Fisher's real life example. A colleague of Sir Fisher claimed that she could tell while drinking tea with milk what is poured in the cup first, it is milk or tea. So, a person is drinking a cup of tea with milk. So, while making the tea, one can put milk first in the cup or one can put tea first in the cup. So, the lady claimed that she can sip and tell which one is poured first in the cup. So, an experiment was designed to test her claim. 8 cups of tea were presented to her in a random order. 4 of these had milk poured first, while the other 4 had tea poured first. So, these are the two populations. There are 4 cups of tea and these are 4 populations where tea is first poured. So, this is milk poured first and here tea poured first. So, she was told that there are 4 cups of each type and she has to sip and tell whether milk was poured first in that cup or tea. She does not know which cup is coming from which population. So, the following data shows that she was right 3 out of 4 times on both types. So, does this evidence support her claim? That means, out of these 4 she could rightly guess for 3 that milk was poured first, but suppose for one of them she was wrong, and similarly out of these 4 she could tell that for these 3 tea was poured first, but for the 4th one or one of them again she failed. Does this evidence support her claim? That means, we are checking whether she is randomly guessing or she actually could decide whether milk was poured first or tea. So, the table that we get is actually milk is poured first in this 4 cups, tea was poured first in this 4 cups, and she guessed that milk was poured first for 3 out of them and 1 out of these, and naturally the other 2 values are fixed and the column totals are 4 and 4. So, very simple table. We have to analyze the data to see whether she actually has any such talent. Now, the potential values of x are 0, 1, 2, 3, 4 and observed is 3, which is the number of cups with milk poured first that were correctly guessed. The only other table with the same marginal totals more extreme than the observed table is the following, that she could guess all 4 correctly and she could guess all 4 correctly that is 4 4, and the exact p value is the sum of the conditional probabilities for these two results, which is 0.2429, because for the first one it is 4 C 3 multiplied by 4 C 1. Out of these 4 she could correctly guess 3, that is 4 C 3. Out of these 4 she could correctly guess for 1, she could guess only for 1, that is 4 C 1, and for the extreme one it is going to be 4 C 4 multiplied by 4 C 0, and of course, the total number of possibilities is 8 C 4. The result is coming out to be 0.2429. Hence, for level of significance 0.05 and 0.01, we cannot reject the null hypothesis, because this value is pretty high. That is, there is not sufficient evidence to suggest that Fisher's colleague has any special power to determine whether tea or milk was poured first in the cup. However, if we test for 25% level of significance, then we could reject the H naught and we could say that actually she is not guessing, she really has the talent to identify which one is poured first. Okay, students, let us now move to one of the most prominent or important non-parametric test, which is test of equality for k independent samples when value of k is strictly greater than 2. So, it is a natural extension of the 2 sample problem to k sample problem when observations are taken from k different populations, such that the jth population has CDF f j, the size of the jth sample is n j, and the total number of sample is n, which is n 1 plus n 2 plus n k. These samples are taken independently both within sample and between the samples. That means, suppose these are the populations, we have taken n 1 samples from here, n 2 samples from here and n k samples from here. So, this sampling is taken independently while taking from the population, as well as they are all independent of each other. The null hypothesis to be tested is that all the k samples are drawn from identical population. That means, we want to check if all of them have the same distribution. Hence, we have the H naught is that f 1 x is equal to f 2 x is equal to f k x for all x, versus all populations are not same, that means they do not have the same distribution. So, we can rewrite it in the form f 1 x minus theta 1 is equal to f 2 x minus theta 2 is equal to f k x minus theta k, such that under the null hypothesis theta 1 is equal to theta 2 is equal to theta k, and under the alternative there has to be at least one pair theta I theta j which are not the same, because if they are same for all of them, essentially we are getting H naught. So, this is the null hypothesis, this is the alternative. We are testing if we can accept or reject H naught. In classical statistics, typically for this problem one uses analysis of variance F test for one way classification. The underlying assumptions for this test are that the k populations are distributed as normal. As you all know that under parametric setup we assume normality with same variance, but mean shifted, and the relevant statistic for them is F statistic, which is the mean square between the samples divided by mean square within the samples. What does it mean? It means the following, that for the ith population we are looking at the mean of the ith sample, which is xi bar, and we are looking how much different it is from the overall sample mean considering all the samples. So, xi bar minus x bar whole square, and that we are multiplying with ni, because there are ni many observations from the ith population, and that we are summing it over I is equal to 1 to k, and we are dividing by k minus 1, because all k of them are not independent, because the total population is constant. So, therefore, if we know n 1, n 2 up to n k minus 1, then n k is fixed. And in the denominator we have the overall sample variance sigma xi j minus xi bar whole square, that is the variance for the ith population, and that we are summing for j is equal to 1 to ni for the ith population and I is equal to 1 to k. We are not going into the details, but the corresponding statistic will follow f distribution with k minus 1 and n minus k as its parameters. Now, f test works robustly if the sample sizes are equal, but it does not work well with unequal sample sizes. That is one of the problem of parametric setup on the top of the normality. However, in non-parametric scenario, the only assumption required is that the underlying distribution is continuous. That is one assumption that we have to make for non-parametric treatment of the above problem. So, there are several tests on the basis of the same principle. The first we are going to discuss is called the Kruskal-Wallis test. As I said, it is a very important non-parametric test, and it works as follows. Given n samples taken from k classes numbered 1, 2, 3 up to k, let the number of samples from the jth class be n j, as we have already defined, and therefore, capital N, the total number of samples, is equal to summation over j is equal to 1 to k n j. What we do in the Kruskal-Wallis test? We do the following. We are testing if theta 1 is equal to theta 2 is equal to theta k, and it is computed as follows. Under H naught, all the n samples may be considered to be coming from the same population, as you all know. Hence, in an ordered list, all the n samples are equally likely to get any of the ranks 1, 2, 3 up to n. That means, what we are doing? We are arranging all the capital N many observations in ordered way. Now, if all the distributions are equal, then any one of them can come from any one of the population. Hence, expected rank of each element is going to be n plus 1 by 2. That we all know, there are capital N many observations, and therefore, the mean is going to be n plus 1 by 2. Therefore, the expected sum of ranks of all the samples belonging to the jth class is going to be n j multiplied by n plus 1 by 2 for all j is equal to 1, 2, 3 up to k. Because each element has the average rank this under the null hypothesis, therefore, the total sum of rank is expected to be n j times n plus 1 by 2. Now, let us calculate actual rank that we have got from the sample. Let R j denote the sum of ranks of the samples belonging to the jth class. Therefore, under H naught, the total sum of square of deviation from the expected values will not be too high. Therefore, an appropriate statistic is going to be how much the expected sum of rank is different from the obtained sum of rank. So, we are making the sum of the square of the differences for I is equal to 1 to k. So, that is in some sense giving us the idea of how much it is varying from equality of distribution. For Kruskal-Wallis test, the statistic used is 12 upon n into n plus 1 summation over I is equal to 1 to k r I square upon n I minus 3 times n plus 1. Let us remember that we are not going to derive it, and this can be shown that is distributed approximately as chi-square with k minus 1 degrees of freedom. As we all know that chi-square is having this type of shape. Therefore, we shall reject the null hypothesis if the value obtained is too high. That is also intuitively clear, because somewhere we are looking at R I minus the expected sum of rank whole square. So, if that value is too high, then we are going to reject the null hypothesis. Thus, one may obtain critical region from the chi-square table. Also, there are tables showing the critical regions for different k. Kruskal-Wallis table are available. Consider for illustration the following taken from this source. Let us go to the table first. So, it looks like this. These are the alpha for several values of alpha. The values have been obtained, the right tail probability for H, and the segment that I am showing, it is for k is equal to 3, and the highest number of observation for at least one class is 5, and therefore, these are different combinations 5 to 1, 5 to 2 up to 5 5 5. In particular, say consider 5 5 4. What does it mean? That means that there are 5 observations from one class, 5 observations from another class, and 4 observations from the third class. If that is the type of observation, then the critical value for 5% level of significance is 5.666, and for 1% level of significance is 4.523. Similarly, for any combination of this type, for k is equal to 3 and the highest observation from any class is 5, for example, 5 4 3, that means there are 5 observation in one class, 4 observation in another class, and 3 observation is another class. Then the critical values are going to be for 5% level of significance 5.656 at 5% level and 4.549 at 1% level. So, that is how we need to read the table. Now, let us go back here. Each table entry is the smallest value of the Kruskal-Wallis H such that its right hand tail probability is less than equal to the value of alpha given as the column header for k is equal to 3 and each sample size is less than equal to 5. Similar tables are available for larger values of k also, but in practice one can approximate that with a chi-square distribution. Therefore, the critical values obtained for a chi-square table can be used here, when for a particular case the degrees of freedom is going to be k minus 1 when k is greater than equal to 4. Kruskal-Wallis test has the following characteristic. Its distribution is approximately, but not exactly chi-square. You have to remember that it is only an approximation to chi-square. It is applied when the data is not normally distributed, as we have mentioned many times. Average ranks have to be used when there is a tie. If two observations are coming to be the same, then as usual we have to give them the average rank. It is used when k is greater than 2 and degrees of freedom is coming out to be k minus 1. So, let us give an example. Consider 3 class problems C1, C2, C3. There are 5 observations from one class, 5 observations from the second class and 4 observations from the third one, and the values given are like this 79, 13 up to 90, and you can see that these are the 14 values given 5 plus 4 plus 5 as coming out from the 3 classes. We need to test whether these can be considered to have come from the same population. So, what we did? We have ranked the combined population, and under this ranking, these are the ranks. This is getting the rank 9, 10 is the smallest, therefore, it is getting the rank 1, and similarly you can see 13 is getting the rank 2, 28 is getting the rank 3, 36 is getting the rank 4, like that. Highest one is 94, which is getting the rank 14. Therefore, R 1, the sum of ranks for the first set is 37, R 2 is 45 and R 3 is 23, when N 1 is equal to 5, N 2 is equal to 4 and N 3 is equal to 5. Therefore, R 1 square is coming out to be 1369, R 2 square is coming out to be 2025 and R 3 square is coming out to be 529. Therefore, we are dividing them by corresponding number of observations. Therefore, R 1 square by N 1 is equal to 273.8, R 2 square by N 2 is equal to 506.25 and R 3 square by N 3 is equal to 105.8, and therefore, the sigma R I square upon N I is coming out to be 885.85. Therefore, the value of the Kruskal-Wallis statistic H, for which the formula is given, already I have given it to you, is coming out to be 12 upon 14 star 15 sigma R I square by N I, which is coming out to be 88.5.85 minus 3 times 15, which when we simplify we are getting 5.62. As I have already shown to you that this value is coming out to be 5.666, that is the critical value at 5% level, and 4.523 the critical value at 1% level. Therefore, what decision we can arrive at is the following, that since 5.62 is less than 5.666, therefore, the null hypothesis is accepted at 5% level of significance. However, it will be rejected if we test at 10% level of significance, as the cutoff value there is 4.523, that is less than 5.62. So, basically what we are saying, if we get a chi-square type of distribution at 5% level, we have 5.666, at 10% level the cutoff is 4.523 and our observed value is somewhere here. Therefore, we cannot reject the null hypothesis at 5% level of significance, but we can reject the null hypothesis at 10% level of significance. Let me now talk about another test which is called JT test, named after these two scientists. It is similar to Kruskal, but there is a difference in the treatment of the alternative. So, the setup is same. We have n I many observations from the ith population, I is equal to 1 to k, and we have k many continuous populations with the corresponding distribution functions as f 1 x, f 2 x up to f k x. Suppose we want to test whether theta 1 is equal to theta 2 is equal to theta k against the alternative hypothesis that the location parameters are not all same. Therefore, in JT test the alternative is written in the different way, as I have already said. Here alternative is written as follows: H 1 is that theta 1 is less than equal to theta 2, less than equal to theta 3 up to less than equal to theta k. That means, we are looking at the location parameters in an increasing order of magnitude. Note that under the location model, when theta I is less than theta j, the population corresponding to f j is stochastically larger than the population corresponding to f I. So, pictorially what we are looking at, suppose this is how f 1 is distributed, and similarly then f 2 is distributed something like this, which is stochastically larger than that one. Similarly, for f 3, which may be somewhat like this, like that the distribution of the k populations, we are trying to check if the null hypothesis can be rejected against this type of a alternative. This alternative, now actually what we do, we divide it into k into k minus 1 by 2 many inequalities of two populations. We were doing it in the following way. We were looking at theta 1 is less than equal to theta 2, theta 1 is less than equal to theta 3, up to theta 1 is less than equal to theta k. So, these are the inequalities corresponding to theta 1. With respect to theta 2, what we are trying to check, if theta 2 is less than equal to theta 3, less than equal to theta 4, and theta 2 is less than equal to theta k. Finally, corresponding to theta k minus 1, we are just checking theta k minus 1 less than equal to theta k. That is what we are saying, that each time we are just considering only two populations and we are trying to compare their location parameters. Hence, the problem of testing H naught against H 1 may be viewed as a collection of test problems, each of which is a two sample problem. I hope the concept is clear, and of course, we have to understand that at least one of the inequalities have to be strict, because if all inequalities become equality, then it is nothing but the null hypothesis. Now, JT test uses Mann-Whitney statistic Uij for the two sample problem comparing the samples I and j, where I and j belong to 1 to k with I less than j. The overall test statistic therefore is constructed by adding the Uij's in the following way. This is equal to U12 plus U13 up to U1k plus U23 plus U24 plus up to U2k plus Uk minus 2 comma k minus 1 plus Uk minus 2 comma k plus Uk minus 1 k. So, since we have k into k minus 1 by 2 many different pairs, therefore, we have to compare for all of them and we have to obtain the corresponding Mann-Whitney statistic. Therefore, the final statistic is the sum of this sigma over I is equal to 1 to k minus 1, j is equal to I plus 1 to k u I j. As you can easily understand that this expression can be written neatly, concisely like this. Question is how to compute u I j. We know that the u statistic for two samples x and y in effect checks the number of times an x observation is less than y observation. That is, I is equal to 1 to n, j is equal to 1 to n, indicator of x I is less than y j. Therefore, we are looking at all pairs x I and y j and we are checking how many times x I is less than y j. I is indicator variable, that means that if this is true, then I is equal to 1, otherwise I is equal to 0. So, I am giving a slightly different notation, so that if you do not get confused, I am telling you that in lecture 3 we have defined u statistic as the count of number of times that y observation is less than x. So, that is what we have done there, and therefore, we got this formula. If you want, you can go and check with your lecture note 3, but here the difference is that they are ordered. That means, when I am talking about x I and x j, basically I is less than j. So, this ordering we are maintaining to give it a convenient notation for JT test. Accordingly, the Mann-Whitney statistic Uij for ith and jth sample is R is equal to 1 to Ni, S is equal to 1 to Nj, because these are the number of samples from the ith and jth population respectively, and we are looking at the corresponding value whether it is less than or not, where xir is the rth observation in the ith sample and xjs is the sth observation in the jth sample. Therefore, finally what we get, B is equal to sigma over I is equal to 1 to k minus 1, j is equal to I plus 1 to k, this we have already seen, and this part is replacing Uij from here, and this complicated expression gives us the value of B, the statistic. The rejection region is large values of B, because if H1 is true, observations from the jth sample will tend to be larger than observations from the ith sample. The JT test rejects H0 against the ordered alternative H1 when B is significantly large. Thus, the exact p value is coming out to be probability of B is greater than equal to some small b under H0. Therefore, the appropriate rejection region is going to be B is greater than equal to some value which comes as a function of alpha, k and also n1, n2, nk, such that the probability that B is greater than equal to this value has to be less than equal to alpha under H0. However, for larger samples, in practice it is more convenient to use an approximate test. If Ni by capital N tends to be some constant between 0 to 1, the distribution of the random vector u1 to u13 up to uk minus 1 comma k under H0 can be approximated by a k into k minus 1 by 2 dimensional normal distribution. So, it is a multivariate normal type of distribution, and the expected value of B is coming out to be n square minus sigma ni square whole divided by 4, and variance of B is coming out to be n square into 2n plus 3 minus sigma ni square into 2ni plus 3 whole divided by 72. We are not going to derive this here, there is no scope. However, we know that when value is large, then B minus expected value of B root over variance of B can be considered to be a normal approximation, where expected value of B and variance of B can be found out without going into the detail, simply from the values of capital N small n I is equal to 1 to k. And once we are going to use a normal test, we shall check if B is greater than equal to expected value of B plus z alpha, which comes from the normal distribution multiplied by the standard deviation, that is variance of B to the power half, that is the square root of the variance. So, that is how we actually conduct the test to check if we can accept or reject the null hypothesis. Okay, friends, with that I come to an end. Over the last 10 lectures, we have studied a large number of major non-parametric methods for testing different hypotheses on populations on which normality assumptions is not valid. The tests are very intuitive and gives us a lot of insight into what can be derived when the sample size is small. Consequently, they have huge potential for data science applications, and I hope that all those who attended, whether a teacher or a student, they will be benefited from this series of lectures. And this is my sincere respect to all those great brains who have thought so nicely and who could get so much out of small sample size. That is truly amazing and truly inspiring for all of us. So, this series of lectures is from my side as a homage to all these great minds. Finally, This series could not have been possible without you students really attending and understanding the rather complicated subject. I could make this possible because of a lot of help, particularly from NPTEL people of IIT Delhi, NPTEL of IIT Madras, and last but not the least, my teaching assistant, my student Kushagra Tandon, who understood the concept in a very short period and helped me throughout in preparation of the lectures and framing the questions for all of you. I hope you solve the problems and get the beauty of non-parametric statistics. Thank you.